Hi, and welcome back. This is the third in the series of the 3.2.6 beam design videos. So uh, in this video, I'm going to show you how to use the allowable strength design method. And this is probably the most confusing part, if only because of all these, you know, all these terms, M sub n, M sub a. So I cut and pasted these terms over here in this equation, but these are the two equations you're going to need. And you'll notice they share a variable. So this is what we're going to have to do first, and then we do this, and then the final goal here is to look up. Is to obtain a ZX. ZX is your plastic section modulus, and then this is what you look up in the table. Okay, so let's unpack some of these terms. M sub n is what they call the nominal moment, right? Nominal. You've heard that word before. And the M sub a is what they call the allowable moment. In fact, this is what what you calculated before. M, the maximum moment that you calculated in the previous step. We called it M sub max. And this is your safety factor of, in the case of bending moment, it's 1.67. So this is a 1 2/3, right? It's rounded to the decimal. So this is the first equation you're going to plug in, and it's a really straightforward equation, but you have to understand we're using the maximum moment we obtained in this step, 40,500 foot-pounds, times the safety factor to give us the nominal moment. So what that looks like is M sub n equals 40,500 times 1 2/3, 1.67. 1 2/3 is 5/3. And again, the reason I do that is because the 3 cancels easily and, nicely. And you're left with 67,500 foot-pounds. Okay. So that's pretty straightforward. Nominal moment, it just includes a safety factor. Now, step 2 in this, 4A, we're going to have to do allowable strength design for shear as well. So that's why I called this 4A. This is just for the bending moment, because we have to make shear and bending are two very different types of forces. So we have to make sure our beam is going to be able to withstand both of those. So now we have to rearrange this equation on the right, number 2 here, because what we are looking for is Z sub X, the plastic section modulus. So I'm just going to rearrange that here. Zx is just the nominal moment divided by the yield stress of steel. Now, they gave us that yield stress of steel earlier. I showed it to you earlier from the first part of the assignment. And now the important part of this is making sure you do your dimensional analysis. So here's the nominal moment we determined here. It's foot-pounds. So foot-pounds. I'm going to write those in. I'd even write them in different color here, just so that it's clear. Let's make sure we do our dimensional analysis in purple. So this is feet times pounds. Now, 50,000, the yield strength of steel, is actually pounds per square inch. And that's in the denominator. So 1 over square inches is square inches. So that square inches in the double denominator. I don't have to ask Mr. Turner what he calls that, but that term is going to go up to the numerator. But notice we now have feet and inches squared. That's not good. So we do need to throw in a conversion factor here, because we got to get rid of these feet. We're going to do 12 inches per feet in the numerator. And that'll help us cancel out the feet. The inches squared, the pounds will cancel too, right? Pounds over pounds. The inches squared, because it's 1 over inches squared, that flips upside down. Inches times inches squared are going to give us inches cubed. And if you look at the table, you'll see the unit for the plastic section modulus is indeed inches cubed. So now we're good with the numbers. And if you do all that multiplication out, 67,500 divided by 5,000 times 12 will give you a, I believe the Z of X, the plastic section modulus of 16.2. So what we need to do is then go and look up in that online table and find a wide flange beam that has a section modulus, plastic section modulus, that's the full term for it, around the x-axis, right? Make sure you're looking at the right, because we're bending up and down. That's bending around the x-axis. It's got to be greater than 16.2, but we don't want it to be a lot bigger than that. So that'll be the next step, is looking that up in the table. That should be pretty straightforward. I'll leave that up to you. In the next video, we're going to check the allowable strength, use the allowable strength design method to check the shear.